Hello, in this lecture today I want to continue to talk about postgraphs and look into one variant of postgraph-based SLAM, which is an hierarchical approach. So the key idea is to not use a standard postgraph, but a hierarchical version of it, which has certain advantages, especially if it comes to online mapping and the goal of saving computational resources. The reason for this is that the hierarchical postgraph is kind of a simpler problem than the original postgraph problem, or an approximation of the original problem that can be solved in a more efficient manner. Before we start with that, let's very briefly recap what postgraph SLAM was about. So the idea was to represent the problem in the form of a graph, and this graph consists of nodes and of edges. And every node represents a pose, typically a pose of the robot. So this can be in the 2D plane X, Y, and an orientation theta, and if you're in the 3D world, that would be X, Y, Z, and 3 rotational angles, yaw, pitch, and roll, for example. So the robot moves through the environment, which we can see here. So the blue triangles are poses of the robots at a certain point in time, and those small arrows over here represent those constraints or soft constraints. And those soft constraints give us some information how those poses should be separate from each other. So they describe a transformation between those two poses. They are inherently uncertain, and they typically stem from observations or from odometry measurements. And while the robot is moving through the environment, it creates new poses, creates constraints between those poses, and whenever the system re-enters a previously known area, so it closes a loop, we add additional constraints also between non-successive poses. And the overall SLAM problem is represented through this graph, and we typically use the least squares formulation in order to find a new configuration of the nodes in this graph that minimizes the squared error introduced by the constraints. So in sum, in postgraph-based SLAM, we have a graph that represents a problem, and the important thing in the postgraph is that every node is a pose. General SLAM graph may also have other entities, such as landmarks, for example, but here we are looking just into postgraphs. So a node in this graph corresponds to the position of the robot at a specific point in time, and an edge, which typically connects always, not always, typically it connects always two poses, represents a spatial constraint between them. And this spatial constraint results from a measurement or from odometry information. And the goal of graph-based SLAM is now to first build up that graph and then find a configuration of the graph, that means a configuration of those nodes, so that the overall error from the constraints is minimized. And we are typically looking here into squared errors or some robust variants of this. And this is a so-called back-end part of the SLAM problem. The front-end part takes a sensor information and builds up that graph, and the back-end performs the optimization or error minimization that is involved in here. So there are two parts in this, the graph construction, which is the front end, and the graph optimization, which is the back end. But it's important to note that there's actually an interplay between them. So because we typically generate these constraints and data associations in the front end, which generate new edges, and then the post-graph optimization will actually find a better configuration of those nodes. So a configuration that is closer to reality. And so then the front end gets this update. But if the front end has actually a better map, it's also likely that it will make better data associations. So it can exploit the steps of the optimization in order to make better data associations. With better data associations, we will get better maps. And so it's a cycle which has the potential to improve the map and improve the data association at the same point in time. As a result of that, we typically need intermediate poses. So it's often not enough to just collect all the data and then run everything, the optimization, only once in the end. Typically, we are interested in actually running this optimization in an online fashion and always provide the platform or the robot or the autonomous car with the best possible map at the current point in time. And this is kind of the standard graph-based SLAM problem so far. And so the idea of a hierarchical postgraph is now to generate a simplified version of that graph, which has a smaller number of nodes and a smaller number of edges, but which is a good approximation of the original problem. So by solving this simpler problem, we actually have results faster, and maybe even in situations where we have a smaller number of local minima and can perform a better optimization here. So you can envision the hierarchical postgraph in the following way. Let's say we have here nodes which sit on a sphere, so it's very easy to visualize and also very easy to see if the map is consistent or not. You can see this as a robot basically traveling all over the world. And then this could be the bottom layer, so the original post graph. This is still encoded in the hierarchical post graph. And then at a first layer, I could simply have a much smaller number of nodes. Let's say one node in this post graph represents 10 or 15 nodes in the lower post graph. Then I can even go a step further and make another abstraction layer where, say, no, one node over here actually represents a local area in here, which again resembles, let's say, 100 or 1000 different nodes. And then I can take this, of course, further and further until I basically have a single node. And the idea is that optimizing this graph, for example, should be faster and easier than optimizing this graph or this graph. So quite often it may be sufficient to just optimize on that higher level to get the kind of global topology solved, and then use this, for example, for solving our data association problem. And the key insight in here is actually that we do not need to optimize the whole graph whenever we obtain one single new observation. This can be needed in case of a large loop closure, that all nodes are actually affected, but that's actually very seldomly the case. So much more often we have the situation that we add a new node, but we actually do not need to change a lot of the graph configuration because this single new observation has very little impact on the other parts. And the second thing is that for performing loop closure, we typically do not need to have the perfect map where everything is perfectly aligned. We just need to have a good idea about the topology of the scene and maybe locally consistent maps. So for loop closures, let's say we have a robot which drives around in the environment. Let's say it starts here and drives along this trajectory, so it will actually generate this post graph as it can be illustrated over here. So the robot is now over there and now says, okay, where do I need to check for loop closures? So nodes in the graph that I may need to inspect in order to see if we actually find a loop closure. And for that, we need to have a rough idea about two things. First, what the world looks like, so what's the overall topology of the scene, and we also want to have information about the uncertainty of the involved nodes. So the robot may needs to know, given this is the center of the reference frame, what is my uncertainty right now, so they can see which nodes are actually overlapping with my, for example, ellipse illustrated by the covariance matrix, like this one over here. If that's the uncertainty of the robot, then let's say the 3 sigma bounds, for example, then the robot may only need to inspect those 3 poses over here to cover 99% of the probability mass of possible locations where it is, and doesn't need to check with the whole graph structure. So if the robot would need to verify loop closure, look for loop closures, looking only on these red nodes or among those red nodes is actually a smart way to do. It first will be much faster because you have a smaller number of nodes to inspect. And it will also reduce the number of data association mistakes you're potentially doing. Because it could be the case that we have another area where the robot has been, let's say, example, this node over here, which looks very similar to its current node. And so there's a potential of making a data association mistake just because the world looks similar in 2 different places. And as a result of that, constraining the search into the area where the robot could actually be from the uncertainty propagation through the graph is actually a smart idea. So the hierarchical approach tries to provide an intermediate solution or temporary or approximate solution, let's say, of the original post-graph problem so that we can actually answer those questions over here. And that's what it is all about. So the insight is for finding loop closures, we typically don't need a perfect map. We just need to know the topology of the scene, and also for navigation tasks, for example, the robot always or often just needs to know the rough topology of the scene and maybe a more accurate local map. But this is actually a very local thing. In its local surrounding, let's say the next 10, 20, 30, 40, 50 meters maybe in its surrounding, it wants to have a good map. But if the map outside that area is slightly inconsistent or not perfect, it actually doesn't really matter that much in most tasks. So the key idea of this hierarchical approach is to perform an approximation of the original post graph and correct only, let's say, the core structure or the overall topology of the scene and not every single node in the post graph. And this also exploits several other facts that we can observe in these robotic problems. The first thing is the robot is not jumping around through the environment, cannot be teleported to other locations. Typically, everything the robot does is very local. So by optimizing only its local map, it is typically in that area where it is and will have a good map of the environment, and we just need to have a rough idea about the topology in order to check for loop closures. And the second thing which is important, we typically have sensors which have limited range. So a laser rangefinder just sees in its local surrounding, let's say 30 meters around the robot. So we don't the number of nodes it may impact just by observing the same part of the environment is actually limited by the sensor range. So we don't need to inspect the whole world in order to get everything right. So let me explain you now very informally first how this idea of the hierarchical post graph actually works. So let's say we have an input post graph, and this is kind of the full dense post graph that we have. And it's a structure which, for example, looks like this. So the first thing we want to do, we want to actually group nodes together and form kind of, let's say, local areas in this post graph. And I just illustrated this here. We just have some groups shown by these dotted circles. And the idea is now that we kind of put nodes together and in that graph, and they kind of seen as a local map or local area. And the key idea is in the end to represent, to treat those local areas as kind of small local maps, and don't change the map in between, but just keep it as a kind of rigid map. And there are different ways how we can form those groups. This can be very simple criteria, such as whenever the robot traveled more than 50 meters, we just create a new local submap. We may have smarter ideas if we can determine, for example, intersections in an environment. We may break it down within intersections or any other technique we want to use. But my experience is often a very simple threshold, like we have moved more than 20 meters or something like this, is a very good starting point. It's very easy to implement, easy to debug, has a very small number of side effects and performs pretty good. So there's no reason typically to do something substantially more complicated. What we then do, for all of those groups, we actually select one representative node, here shown in red. So every of those red nodes, I say, okay, you are the node which now represents the local map. So we can see this as the other elements in this local map depend on that map. So the idea later on will be, if I move this red node, the other nodes should actually move with it. So we can see this as a representative. And those representatives are now the nodes which we can take to the next level, one level up the hierarchy. So in the next upper level of the hierarchy, we will basically forget about the green nodes over here and only consider the red nodes that we have. And only the red nodes kind of are the next level of the hierarchy. So I can just kind of take that up now, and then it would actually look like this. Note that the connections, if I go back, so if two groups are connected because the elements of their group are connected, this edge also should be connected on the higher level, like this edge over here. So this is now a simplified version of this original graph, a more sparser version, a version which has less nodes and less edges. And now we need to work on this upper level. So what's important on this upper level? First, the edges on this upper level should reflect the connectivity of the groups of the nodes. So if two groups of nodes are connected with each other, also their representatives should be connected on the upper level. And what we now need to do is we need to actually find the parameters of those nodes, especially those edges. Nodes is easy, edges is more complicated, of this higher level. Why are nodes easy? Because those nodes on this higher level are exactly the representatives I've chosen on the lower level. So it's exactly the same entity. So there's nothing I need to do about it. I need to, however, invest a little bit of brain power in how to compute those edges on the higher level, because the edges itself do not directly exist, at least. And then I created the next level of my post graph. And I can, of course, repeat this process in a recursive fashion. So now I can again group nodes and raise them up again to the next level. So I can recursively repeat the process depending on how many hierarchies I want to have, depending on how large my problem is. And now consider we are on one of those higher levels, and now we want to perform an optimization on this higher level, which has a smaller number of nodes and therefore should be much faster to execute. So we are on this upper level, and now we optimize this upper level completely. So let's say we perform our optimization, and this is the result of our optimization process. So now what happens, we actually move the representative nodes for the lower level. So we optimized all nodes on the higher level. Every node on the higher level is a representative node on the lower level. And so we're basically shifting the representative nodes in those groups on the lower level as well. And the question is, what are we going to do with the other elements of the group? And here, the idea is the following, that if you look, for example, to this group over here, let's say this is a current robot position, we take those nodes which have been originally connected to this representative node and move it in exactly the same way than the nodes on the higher level. Or we can use other strategies. If you are thinking about local navigation, we may only take the nodes where the robot currently is and optimize the group downwards, taking this into account. Maybe ignore the rest on the lower level. So there are different variants of what I can do and how I can actually perform this form of relaxed optimization. But at some point in time, I may want to go down to a lower level, and then I have the ability to kind of shift the representative nodes, shift the connected node in the group as well, which will lead to some inconsistencies, but this is something I can then fix and still have an easier to solve problem on that lower level. So a few words about the construction of this hierarchy. How does it work? So the first thing you may want to take into account is, when should we actually create a new group? How should that happen? And again, as I said before, typically a very simple threshold-based decision does a really good job. So whenever the robot traveled for, let's say, 20 meters or something like this. Other options could be that if you have some additional knowledge, some additional information, maybe some topology information, you may exploit that, but often my experience is that not really needed. And when you're creating a new group, because you finished your first group, you select one of the nodes as a representative. It can be simply the first one, can be the one which is closest to the center of mass, could be the one which has the highest number of edges. For now, we just take the first one, but there are other options that you can do as well. And the next question is, when we optimize in the higher level, when and how should actually information be propagated downwards? The how we will explain, and the when, the easiest answer to the when is when your map gets inconsistent. So if the optimization on the higher level changes a node substantially, so substantially shifts a node, then it's a pretty good indicator that something in the local map, in these local groups, will change similarly strongly. And then we may propagate this information downwards. If we just move the top node by a few millimeters, often we don't care. And we can just say there will be some minor inconsistencies on the lower level, but the effect is actually really small. So nothing that I actually need to do right now. And then the key questions are, how are we actually constructing these edges on the higher level in the graph, so the sparsified graph, and how actually should we propagate the information downwards? And that's something that we will now discuss in the next couple of minutes. So how do we construct the edge and how to propagate information downwards? Okay, so let's go. How do we do the edges? So what we have, if we want to create an edge on a higher level, we basically have two groups of connected nodes. So consider our initial example. These were kind of these two groups of nodes. Both have representative nodes, here shown in red. And then what we want to do is we want to turn this problem into that simplified problem on the higher level, where the representative nodes stay the same, and we want to create this edge. So the question is, how can we fuse all the information which is stored in that group to be stored in this edge Z here? And again, we typically cannot add all this information, so this is often an approximation, what we are actually doing here. So how to compute this virtual observation, that which relates the two poses in terms of a mean and the information matrix associated to this, so that I still have a post graph on that higher level with the appropriate edge representing that problem. Okay, how do we do that? The first thing we do, we kind of take those two groups out of the optimization problem and turn them into a small own optimization problem. So I'm basically taking all those nodes in here and ignore all the rest which was there and perform an optimization just of these two groups. So I'm optimizing these two groups. What does it mean? What the result of that? The result of that is the optimal solution, assuming only those two groups exist and nothing else. Okay? So that means we have now a local configuration of these two, of all the elements of all the nodes in this small group, so that we can then derive a virtual measurement from that. So the observation about the relative transformation between two poses is then directly given by the configurations of the nodes in this optimized subset. So I perform the optimization in this subset of nodes, and the resulting solution directly allows me to compute the configuration XA and XB, how I call them now, and then XA and XB, the relative transformation between them, directly gives me the mean constraint, my Z. In addition to this, I want to have uncertainty information. I want to have the information matrix associated to this constraint, because I need to know how much information is stored in there. And again, that's something that we can do as well, given what we have learned in the past about postgraphs, basically computing an uncertainty of a node with respect to another one. So let's say we want to compute that we say, assume this one to be fixed, so what's the uncertainty to go from A to B? So what we can do is we fix, in the small optimization problem, this node, so we take that node out, invert our H matrix, and then take out the corresponding block that represents the node XB and invert this small part. So this was the end of the previous lecture on postgraphs, the 1 or 2 slides explaining how we are computing these uncertainties. So what we are doing is we are the information matrix about the edge from A to B can be obtained by taking the original H matrix, taking out this node, inverting it. That means I get the covariance matrix of the overall problem. I take out the block BB. This is the block which represents the uncertainty of this node, and with respect to this one, and then I invert the whole thing again in order to get the information matrix. So by 2 inversions, basically, of 2 small problems only involving the edges in those groups and the nodes in those groups, we actually obtain the edge parameters. So just by inversion operations, but on small matrices, I'm actually able to obtain the information about the uncertainty that is represent between those 2 representative nodes based on the group information or the nodes stored in those groups. So it's kind of the first part done. And the second question we had to answer is how do we actually propagate information downwards when we're optimizing on a high level, how to bring this information down to the next lower level. And so the thing is we are optimizing on a higher level, and all of those, so this is, let's say, this example over here, just taking out 2 representatives now. Let's say they have moved a little bit further away or closer to each other, depending on the optimization. And the question is, how do we bring this information downwards? And now we exploit the fact that a representative means, on a higher level, means it's exactly the same node on the higher level as well as on the lower level. So it's actually the same entity. So by moving the elements on the higher level, we automatically move them on the lower level. But this only holds for the representative nodes. This doesn't necessarily, or by default, holds for the other elements nodes in the group. But we said the representative node should actually represent the whole group. So what we're doing is we're actually shifting all elements in this group in exactly the same way. So if, for example, this constraint tells me those nodes should move a meter closer to each other, and they move towards each other 1 meter. What we are doing is we're just basically taking all the nodes in the individual groups and move them exactly in the same way. Also shift by 1 meter, so they're moving closer together. Of course, this will lead to some inconsistencies over here. So for example, in this example, the nodes had a certain spacing, and now they're kind of shifted closer to each other. So there's a mistake, so to say, which happens over there. An additional error is introduced. But this is something that we do not care at the moment, because typically those updates are small. And if those updates are small, this may lead to a small inconsistency here in our map, but often doesn't lead to a very serious issue. However, we can check how large this update was. If there was a substantial update, you can say, okay, there's more work which needs to be done in this area. Let's simply go down to the lower level and optimize this part on the lower level as well, or optimize the graph on the lower level, because obviously there must have been changes which affect a large number of nodes in the graph. And we basically propagate this information recursively downwards until there's either we reach the lowest level or the change introduced by the move of the representative nodes was very small. And in this way we optimize, propagate the information downwards as long as we need it. And we may have some constraint to that, whatever. Whenever a node moves less than 3 centimeters, I don't really mind about that anymore. Because, let's say, obviously application specific, but let's say 3 meter shouldn't affect my local map so far. And then I say I'm fine not having the perfect map. Okay? So, and then we are done already. So we introduced this idea of a hierarchical approach graph. We explained how we built the post graph We know how to optimize a certain level, standard postgraph SLAM, and then we explained how to propagate the information downwards. And that's actually all we need to know in order to build such a system. A few notes, if you want to build the best possible map, what should we do then? Because it seems to be still an approximation. We obtain the best possible map if we, in the end, optimize on the lowest level. Because if we run our optimization on the lowest level, we are basically solving the original postgraph problem. Of course, in this case, we may not have saved a lot of computational resources because we're solving the original problem, but at least we're able to do that if we want to have the best possible map. And it actually turns out, if you run these algorithms, that it actually has a positive effect to use this hierarchical structure, even if you do it in offline processing. I'm not really interested in online processing. The reason is that if you go up to a higher level, you have an approximation of the original postgraph, but an easier to optimize problem. And you're optimizing a smaller number of nodes and shifting all the other nodes in an approximate fashion in a similar way than those representatives that you're optimizing. And it typically is the effect that this is much, much faster to perform these operations, and all the nodes come closer to their final location more quickly. And then if you then propagate this information downwards, you kind of have a better initial guess for the optimizations on the lower level, so that even if you're solving the original problem, you typically need a smaller number of iterations overall in order to optimize your maps on a lower level. And so even if it sounds a little bit counterintuitive initially, it can actually be advantageous, at least if you have suboptimal initial guesses. So if your initial guess is already very good, the gain is very small, but often you actually converge quite quickly to the right solution, even if you are far away from the initial guess. And what you typically need for this is just basically one path up the tree and one path down the tree. I also brought you a few examples to illustrate you how that looks like in practice. So what you see here is a picture of the Stanford parking garage that was an image and also the corresponding data set recorded by Sebastian Thran's team early in 2005-06 maybe. During this time, Dirk Handel was involved in this and building a map of the parking garage with the vehicle, and then we use this data to illustrate how we can actually build a map of the environment. So this is the map built by a postgraph, here even a colored drivable and non-traversable areas. And what I want to show you is how this optimization works on different levels. So here we used three levels, I think, and I show the level number 0 and the level number 1, and you see how the postgraph builds up on this level 0, which is the original postgraph, and on this level 1, which represents the approximation of that postgraph. So what you see here, so this is the original postgraph. You see how the graph is built up, and you see here just an approximation of the original graph where you see the representatives, how the road is now driving up in this parking garage on the higher levels. And we can see here how with a much smaller number of nodes, we obtain an approximation of the original problem, and all the optimizations can actually be carried out here on this level number 2, and the information will propagate downwards to this level number 1. So that by optimizing this problem, a substantially smaller number of nodes need to be considered in the optimization problem, and I typically have a faster optimization and come more quickly to my result. Another example from an indoor data set, the Intel Research Lab data set recorded by the group of Dieter Fox in Seattle. And what you can see here, again, two levels, the red and the blue level. Red is the original postgraph and blue is a postgraph on the higher level. And what you can see here, the robot traverses through the same environment over and over again, and we can see how the postgraph here is built up. And you can again see that the blue structure has a smaller number of nodes, often simpler connections in the edges, because they are basically representing what happens on the lower level. And as a result of this, we get a simplified version of the postgraph, and this example only perform the optimization on the higher level, shift the nodes on the lower level in the appropriate way. You see sometimes very small shaking postgraphs when some optimizations are carried out, but all in all, the optimizations are only carried out on the higher levels and only in the end propagated downwards. So if we turn this in the end into a final map, we get the typical Intel Research Lab results that you can see over here. Of course, what happens on the higher level is an approximation of what happens on the lower level. And we need to ask ourselves, how good is our approximation, the one on the higher level? There are approximations because with a smaller number of nodes we do this rigid body transformations, but also the edges that we are actually creating are an approximation because they depend on the current linearization that we had in our original problem when we were building up the higher levels of the hierarchy. So we need to take into account that there are some approximations that happen in there. And for that, what we can do is we can actually check the original postgraph problem and the hierarchical postgraph problem, compute the uncertainties on the different levels, and then compare the covariance matrices and see basically the area of overlap or the amount of probability mass that is covered by one uncertainty ellipse and is not covered by the other one. And we can see, so the critical part in here is actually this information over here. This is the percentage of probability mass which is not covered by the approximation on the higher level. So where you're basically overly confident. And this varies in probability mass something between 0.01% and let's say 3%. It depends a little bit on the problem. So these are kind of just rough numbers. So these are situations where on the higher level we think that the covariance matrix is actually too small or doesn't cover the problem really well. And luckily those numbers are very small because these are situations where I may miss a loop close or may reject something, not considering it, although in the original problem it was possible. And then there's the other thing is kind of what's the uncertainty ellipses which are too large on the higher level, so it's a higher uncertainty than I actually have in reality. And here the values go up to 25%, so some covariance matrix may be 25% bigger than the ones which I would get on the lowest level. So I have a higher uncertainty on the higher levels, but that's typically still okay. So I may need to check a few more nodes when I'm looking for loop closures, but at least I don't miss some. So this is something which is kind of less critical from the point of view. And for this Intel data set, we can actually make this comparison. So there's examples. These are kind of the 3 sigma ellipses which are shown over here, and you can actually see kind of the red one are the actual solution, the correct solution. Then you see what level 1 mistake does here shown in green and what level blue does here in big. And sometimes you have mistakes where they are too large by up to 10%, but typically the probability math that you do not cover here is more in the order of 0.1% in this example. That means still keep in mind that is an approximation of the original problem, but an approximation that you can solve much faster, and often you actually get better results with this approach because you have a better initial guess and can, especially in situations where you have a very bad initial guess, obtain a better results using these hierarchical ideas. So to conclude, what the hierarchical postgraphs do, they provide an approximation of the original problem, but one which can typically solve quite quickly. It supports an efficient data association. Looking for loop closures, we only need to inspect a much smaller number of nodes and can make the decision which nodes to inspect much faster as if you would run the original problem. It's actually designed for online mapping, so to support this interplay of the front end and the back end, so of making data associations and optimizations, not with the intention of always providing the best possible map, but providing a map which is good enough to make all the decisions that the mapping robot needs to do. And the nodes on the higher level, you can also see them as kind of a simplified version of a SLAM problem. And they also have other advantages. So what you can do, for example, if you combine SLAM and planning, you could use this postgraph generated on a higher level, which still contains the connectivity information, so the topology of the scene, to actually plan path on a coarse level, how to move from a place A to a place B in a very efficient manner because you have this hierarchical postgraph. And that's something which can speed up your planning processes if you want to drive an autonomous robot from one place to another place, but by automatically being able to go up the hierarchy, plan on the higher level, and then go down. It's very similar to planning if you go with your car on a highway and you see the highway is the higher level and the small roads is the lower levels. You basically plan a path to the next highway entry. You drive on the highway, then you drive on the highway and you exit the highway at a certain point. And planning on the highway is much simpler, and planning in the city is more complicated. It's a very good analogy to that, and something like this you can also do with these hierarchical postgraphs in an effective way for combining SLAM, for example, with planning. So there are several advantages of these hierarchical postgraphs, not only for the SLAM problem itself, but also for other robotics tasks that you may want to do. And again, if you want to learn more about this, there's an open source implementation of the original approach called Hogman, and you can find that resource online, which tells you in more detail with all the derivations how to build up this hierarchical postgraph so that you're actually able to realize such a system on your own. With this, I say thank you very much for your attention and looking forward to see you soon when we talk more about graph-based SLAM approaches. Thank you very much.